Hey guys, today I want to present a solution for the Swiss IMO Team Selection Test 2022 problem 6. At first, let's have a look on the problem. We have given an integer a greater than or equal to 2, and we have given that this fraction n squared plus 4 to the power of n plus 7 to the power of n all divided by n is an integer. We have to show that this fraction is divisible by 11 then. So at first, notice that n divides n squared, and therefore n must also divide 4 to the power of n plus 7 to the power of n. Since it's always difficult to work with some composite n, a good idea is to consider one prime divisor of n, so let p prime, and p should divide n. And since n divides 4 to the power of n plus 7 to the power of n, this divides 4 to the power of n plus 7 to the power of n, and thus p divides 4 to the power of n and 7 to the power of n. Now, since 4 is divisible by 2 and 7 is divisible by 7, but 4 and 7 are relatively prime to each other, we know that p is not equal to 2 or 7. Now, from this divisibility, we can write 4 to the power of n plus 7 to the power of n is congruent to 0 mod p. This means that 4 to the power of n is congruent minus 7 to the power of n, and now we can divide by 7 because p is not equal to 7, and so we have 4 over 7 all to the power of n is congruent to minus 1 to the power of n. And since 2 does not divide n, we know that n must be odd, and therefore this is equal to minus 1. Now we can square both of the sides, and we get that 4 over 7 all to the power of 2n is congruent to 1 modulo p. Now I want to work with the fraction 4 over 7, and therefore I give this a new name, so let 4 over 7 equal to a, and let's bring all this up to the top of the blackboard. So we already figured out that a to the power of 2n is congruent 1 mod p, and this motivates us to define d as the order of a modulo p. This means that a to the power of d is congruent to 1 mod p, and d is the minimal integer for which this holds. Now we know that since a to the power of 2n is congruent 1 mod p, that d must divide 2n. And also, since a to the power of p minus 1 is congruent 1 mod p, we know that d must divide p minus 1. This together with this get d must divide the greatest common divisor of 2n and p minus 1. Now, it would be nice if the greatest common divisor of 2n and p minus 1 is a small integer, because then there are not too much opportunities for d. So it would be nice if we can choose p in such a way that n and p minus 1 are relatively prime to each other. And this is indeed possible, because if p is the smallest prime divisor of n, so p minimal, then all the prime divisors of p minus 1 cannot divide n. So we have that the greatest common divisor of n and p minus 1 is equal to 1, and now, since p is not equal to 2, 2 divides p minus 1, and so the greatest common divisor of 2n and p minus 1 is equal to 2. And now, since d divides 2, we have that a to the power of 2 is congruent to 1 modulo p. Now we can put in 4 over 7 into a, and we get that 4 over 7 squared is concurrent to 1. This means that 4 squared is concurrent to 7 squared. This means that 7 squared minus 4 squared is concurrent to 0. Now 7 squared minus 4 squared is equal to 49 minus 16. This is concurrent to 0, and 49 minus 16 is equal to 33. So 33 is concurrent to 0, and therefore we know that P is equal to 3, or P is equal to 11, since 3 and 11 are the only prime divisors of 33. Now, if we have a look on 4 to the power of n plus 7 to the power of n, we see that 4 to the power of n plus 7 to the power of n is concurrent to 1 to the power of n plus 1 to the power of n, which is concurrent to 2. If we have a look on this modulo 3, and therefore it is not possible that 3 divides n, and so this case is impossible, and we get that P is equal to 11. So 11 divides n. So now let's look again at our fraction here. We have n squared plus 4 to the n plus 7 to the n divided by n is equal to n plus 4 to the n plus 7 to the n divided by n. And since we figured out that 11 divides n, we know that 11 divides this n here, and therefore it is left to prove that 11 divides 4 to the n plus 7 to the n over n. So what we want to do now is to consider nu 11 of this fraction here, and we have that nu 11 of 4 to the n plus 7 to the n over n is equal to nu 11 of 4 to the n plus 7 to the n minus nu 11 of n. And now we know that n is odd, and we also know that 4 plus 7 is equal to 11, which means that 11 divides 4 plus 7, and so we can make use of the lifting the exponent lemma. So we use the LTE lemma, and this gives us that nu 11 of 4 to the n plus 7 to the n is equal to nu 11 of 4 plus 7 plus nu 11 of n, and here we have minus nu 11 of n, and now the nu 11 of n cancels out, and we get nu 11 of 4 plus 7, which is equal to 11, and this is obviously equal to 1. So we have shown that 4 to the power of n plus 7 to the power of n divided by n is indeed divisible by 11, and therefore we are done.